Question 13a. Consider the curve y equals 6x² minus x cubed. Part 1. Find the stationary points and determine their nature. The following are the marking guidelines for question 13a, part 1. For 1 mark, we have attempts to solve dy dx equals 0 or equivalent merit. For 2 marks, we have finds the stationary points or equivalent merit. And for 3 marks, we have provides correct solution. Find stationary points by solving dy dx equals 0. Now dy dx is equal to 12x minus 3x squared. So we're going to solve the equation 12x minus 3x squared equals 0. To make the solving of the equation a little easier, we're going to divide all terms by negative 3. So we end up with the equation x squared minus 4x equals 0. Factorising the left-hand side, we get x times x minus 4 equals 0, and therefore x equals 0 or 4. The next step is to determine the nature of the stationary points. And we can use the second derivative test for that. So the second derivative, d squared y dx squared, is equal to 12 minus 6x. And when x equals 0, the second derivative is equal to 12, which is a positive value. Hence, the stationary point is a local minimum. When x equals 4, the second derivative is equal to negative 12, which is a negative number. And hence, the stationary point is a local maximum. The final step is to determine the location or the coordinates of the stationary points. So we have y equals 6x squared minus x cubed, which is the original function. When x equals 0, y equals 0. And when x equals 4, y is equal to 6 times 4 squared minus 4 cubed, which is equal to 32. Therefore, 0, 0 is a local minimum stationary point, and 4, 32 is a local maximum stationary point. Part 2. Given that the point 2, 16 lies on the curve, show that it is a point of inflection. The following are the marking guidelines for question 13a, part 2. For 1 mark, we have shows second derivative vanishes at x equals 2, or equivalent merit. And for 2 marks, we have provides correct solution. When x equals 2, the value of the second derivative, d squared y dx squared, is equal to 12 minus 6 times 2, which equals 0. Hence, a possible point of inflection exists at the point 2, 16. The next step is to determine if that point is in fact a point of inflection. So we're going to test around that point. So when x equals 1, the value of the second derivative is equal to 6, which is positive. And when x equals 3, the value of the second derivative is equal to negative 6, which is negative. There is a sign change of d squared y dx squared, or the second derivative, around the point 2, 16. Hence, it is a point of inflection. Part 3. Sketch the curve showing the stationary points, the point of inflection, and the x and y intercepts. The following are the marking guidelines for question 13a, part 3. For 1 mark, we have provides curve with correct shape or equivalent merit. And for 2 marks, we have provides correct sketch. The y-intercept is at the origin, and that is found by substituting x equals 0 into the equation y equals 6x squared minus x cubed. Now the x-intercepts are found by solving 6x squared minus x cubed equals 0. So 6x squared minus x cubed equals 0. We can factorise out x squared. So we have x squared outside of 6 minus x equals 0. Therefore, x-intercepts at x equals 0 or 6. So sketching the curve. Just making sure that a ruler is used for the axes and label the axes. So x-axis, y-axis, origin. This is our local minimum stationary point, our local maximum stationary point, and the point of inflection, and of course the x-intercept of 6. The following is the feedback from the marking center for question 13a. Skills addressed. Showing numerical results in their testing of stationary points using either the first or second derivative. Using tables with labelled arrows indicating x, dy dx and slope when using the first derivative test. Factorising fully before solving dy dx equals 0. Showing their numerical results when completing the testing of points. Stating conclusions by classifying their stationary points. Using a table of values to show the change in sign of the second derivative and hence a change in concavity. Indicating that they were substituting into the second derivative. Showing numerical results to verify their test. Stating a conclusion after their test. Drawing a smooth curve of at least 1/3 of a page, clearly showing important features. Labelling all important features, including intercepts, and labelling the axes. Areas for students to improve include remembering that the second derivative is used to test concavity, not slope. Realizing that the y-coordinate is given in the question, so there is no need to show it. Understanding the difference between a point of inflection and a horizontal point of inflection, and sketching the curve beyond the domain of the features to be shown, including passing through the x-intercept of 6.